So let's start today's session. Hello everyone, this is Tanya. I'm one of the TAs assigned to the aircraft design course taught by Professor A.K. Ghosh. So we'll go over the contents of week 7 and week 8, discuss the assignment questions, and we'll try to do a few problem sums. I'm sorry I cancelled the class last week on Tuesday. I wasn't feeling well. Okay, so let's begin. If thrust to weight ratio increases, then the takeoff distance of the aircraft will it decrease, increase, remain unchanged, or none of these? Okay, so let's try to answer this question. So takeoff distance. Does anyone remember what the formula for the takeoff distance is? Anyone? Does anyone remember what the formula for the takeoff distance is? Try to figure it out, or try to intuitively guess it. What would the value of the takeoff distance be if the thrust to weight ratio increases? Okay, so let's try to do this. So what was the liftoff or takeoff distance? You can take either of those. So takeoff distance is the whole distance, the ground roll plus the liftoff. Okay, so let's try to do this. So S liftoff, we know the equation. So that was 1.44 W square by, I think it was rho G S CL max and thrust, right? This was the equation. How did we come to this? So first we draw a free body diagram of the aircraft. So we assume thrust to be in this direction. We assume drag to be in the opposite direction. The aircraft is moving in this direction. In the opposite direction we have our drag. Now what about the other aerodynamic force? Lift. Lift is produced here. It is opposite to the weight. Okay. Now since it's moving on a ground, we also have a reaction force, R. And since it's moving, we have a force in the opposite direction of the movement. That is in this direction, which is the frictional force. What is this force? It will be mu R into R. Okay, what is mu R? Can anyone tell me what mu R is? This is the frictional force. This quantity here is the frictional force. Can anyone tell me what mu R is? It's the coefficient of friction between the aircraft and the surface, between the aircraft's wheels or the landing gear and the surface on which it's moving, right? Just a minute. Okay. So this is the frictional force between the aircraft and the runway. That is between the landing gear of the aircraft and the runway. Mu R is the coefficient of friction. Okay, so the entire force is mu R into R, where R is the reaction force. Now let's write the equations of motion. We'll write the equation of motion only in the direction that we need to consider here. That is in the horizontal direction. So if we write that, F equal to mdv by dt. Now what is this F? That is thrust minus drag minus this frictional force, which is mu R into R. Now if you write the same summation of the forces, the equilibrium, the equation for force in the vertical direction, you have R plus L equal to W. So R is nothing but W minus L. Now we'll just substitute this quantity here. So what do we get? We do thrust minus drag. Can you just confirm if I'm audible? Am I audible? Can you just confirm if I'm audible? can just put it up in the message chat box or anything. Am I audible? Okay. I don't get any response. No, you're not audible. Okay, okay. Okay. Let me get it closer. I had a throat infection. I'm just recovering from it. Okay. So I'll just go over the questions again. The first question of the assignment was if the thrust to weight ratio increases, the takeoff distance of the aircraft will. This was the first question. Am I audible now? Can you hear me now? Can you hear me? Am, am I audible? Um, am I audible now? Can you please confirm? Still can't hear me? Uh, please do. Can you hear me now? Okay, okay. Thank you. Okay, okay. I'll continue. I'll start from the beginning. First question was if the thrust to weight ratio increases, then will the takeoff distance of the aircraft increase, decrease, or remain unchanged? So, this is the equation that we follow. I was just going about how we derive it. So, from this equation, we can see we can just write it in terms of W by S and thrust loading, wing loading, and thrust loading. So, that will be 1.44 that when the thrust to weight ratio increases, the takeoff distance will decrease. They are inversely proportional. So they are inversely proportional. Okay. So we drew the free body diagram of the aircraft that is moving in the direction of the thrust. So the drag is in the opposite direction. You have a lift force and then which balances the weight. Since it's resting on a ground, you have a reaction force. Just a minute. You have a reaction force, and since it's moving on a surface, you have a frictional force. The frictional force is given by mu r into r, where mu r is the coefficient of friction. And if you write the balance equations at the equilibrium in the vertical direction, you have R plus L equal to W, and you have R equal to W minus L. In the horizontal direction, you have F equal to MA, mdv by dt, where that F is thrust minus drag minus the frictional force. And this R we substitute from our vertical equations. So if I substitute that value here, you get mu R W minus L. Okay. Now we use this equation as V square minus U square equal to 2AS. Since it's starting at 0 velocity, we just have V square. This becomes 0. So we need to find out S liftoff. So that is V liftoff square by 2A. Okay. Now V liftoff, we consider V liftoff to be equal to 1.2 times of V stall. And V stall was 1.2 square root of 2 W upon S rho CL max. Okay, so now we substitute that here, and we substitute also the value of acceleration. We have the force here, so we just have to write our equation as force is mass into acceleration. So acceleration is force by mass. Force is from this equation. This is the force. This is equal to F. So that will be F by W by G. Okay, so we have the weight, and weight by G gives you the mass. Substitute all of these quantities here. You get 1.44 V stall square W by G. W by G, and you have 2 times of force. Force is T minus D minus mu R W minus L. Now you substitute the V stall values. Substitute the V stall value. You have S liftoff equal to 1.44 times V stall square is nothing but the 2 and 2 get cancelled, and you have W square. I take the G below. You have G rho SCL max and the entire force term minus mu R W minus L. Now we neglect this small quantity by assuming it to be around 10 to 15% of thrust, and we use only the thrust component here. So S liftoff is approximated as 1.44 W square by G rho S CL max into thrust. And we write it in a neat form in this way. So that is 1.44 W by S, that is the wing loading. You have G rho S. I missed an S here. S, oh no, sorry. S, we took it above. CL max and thrust loading. So S liftoff is directly proportional to the wing loading, is inversely proportional to the thrust loading, is inversely proportional to the density, is inversely proportional to CL max. So if you were to increase the wing loading, your liftoff distance will increase. If you were to increase thrust loading, your liftoff distance will decrease. This is inversely proportional. If you increase the density, that is, if you go above, your liftoff distance will increase. If your altitude increases, that's what I meant. If you decrease, right? If you increase your CL max, that is by deflecting your high lift devices, if you increase it, the takeoff distance will decrease. Okay, so the answer here is, question was thrust 2, weight ratio, that is thrust loading. If thrust to weight ratio increases, then takeoff distance will decrease because they are inversely proportional. Okay, let's go to the next question. The load factor of an aircraft during transition phase of a takeoff maneuver will be. It has to take off. Okay, so the load factor is N equal to lift by W. What will the load factor be when it's transitioning into takeoff? Greater than 1, exactly. If it's equal to 1, it will hover like a quad rotor. If you need to take to be higher than the weight, so your N will be greater than 1. Your lift has to be greater, it has to compensate for the weight and take off. So lift will be greater than 1, which is why greater than weight, which is why your load factor will be greater than 1. Okay. Next, the ground. Sorry? Okay, but I am required to questions again, so I'll just do that. Just three more, right? I'll just go over that. Assignment 8 will only be discussed on Tuesday. Okay. Okay. So the ground roll distance is related to thrust reversal or the reverse thrust as. So you use the same equation as the previous case, which was S liftoff was equal to 1 point. We'll just write the proportionality here is proportional to W by S by rho G CL max into if the thrust is reversed, you have Sg is directly proportional to W by S rho G CL max, the reverse thrust by W. So the main equation, what changes in the equation that we derived here, all of these will be in the same direction. So the reverse thrust will be in the same direction. This will be T reverse. So this equation will have plus sign here, plus sign here. It will be in the same direction. But the proportionality remains same. So it is Sg is inversely proportional to 1 by distance is related to thrust as, again similar question. So it's inversely proportional to the thrust. As the flap deflected during landing, the ground roll distance will, like we discussed previously, so S liftoff is inversely proportional to CL max. When we deflect a flap, the maximum lift coefficient increases. So if this increases, the lift takeoff distance will, it will be inversely proportional. So if your CL max is increased, that is flap is deflected, CL max is increased, the ground roll distance or the takeoff distance, here it is ground roll, will decrease. Okay, so now let's look over this question. It was a straightforward question from the book, right? So we'll just go over that. If the climb gradient is G, then which of the following is correct? What was the climb gradient? What was the quantity? G. It's G, but what was the equation? What G equal to? Was that what it was? Climb gradient was T by W minus D by W, right? Yeah. So this is nothing but sine gamma. Sine of gamma. So where gamma is the flight path angle. So this was your G, that is climb gradient. Now if you replaced, sorry, sorry. So if you replace this D, so if I just write the equation in terms of D by W, you have D by W equals to thrust upon weight minus G. Now if you substitute the CD equals CD naught plus KCL square into this equation with the, obviously the Q, the dynamic pressure, and then simplify, you get an equation like W by S, that is the wing loading, is equal to thrust loading minus G plus or minus. So you have a quadratic equation in W by S, so you have this solution to it. T by W minus G whole square minus 4 CD naught upon pi E A R by 2 upon Q pi E A R. Now if you need to have real values of W by S, this quantity needs to be greater than 0. So we just write down that equation, that is now we simplify this. So I just take T by W minus G should be greater than 2 CD naught by pi AR square root of it. And what was our equation in terms of it was thrust to weight. Can all of you mute yourselves? Okay. Okay, so if I just write the equation in terms of thrust loading, you have greater than G plus 2 CD naught upon pi E A R. So that is this option. Yeah, greater than or equal to, even if it's 0, you will have real values. So it is the third option. This is the right option. Okay. Next we have takeoff parameter. This was a straightforward direct equation that was mentioned in the lectures. Which one is the right answer? Takeoff parameter, TOP. Which one is it? Which one? Third one. Yes. So it's directly proportional to the wing loading, inversely proportional to the thrust loading. It's similar to the previous equations that we had seen, right? What was the previous equation? The lift off distance. It was similar to that. Directly proportional to wing loading, inversely proportional to thrust loading. Okay. What type of airfoils are generally used in flying wing aircrafts? Are they symmetrical, cambered, reflexed, or none of them? Just flying wing aircrafts. Yes. Okay, and can you tell me why? Okay. Just pay careful attention to the words. It is flying wing aircraft. So the aircraft is just a wing. There are no other surfaces over it. No fuselage. It's just the wing. Okay. So the only quantity you have there, the only structure you have there for stability, everything is just a wing. So now try to answer this. Try to justify your answer if that is still the answer that you're going with. And try to justify it. Why would it be symmetric? Okay. Uh, okay. Why not cambered? If you're saying it's symmetrical, why not cambered or why not reflexed? Try to think of it. It's just a wing flying. Okay, so it has no other surfaces. Try to think about it from the stability or pitching moment or something like that. So when we discussed these airfoils, we discussed its pros and cons. You're right, cambered airfoil produces lift at zero angle of attack and you get lift to take off. That is true. And traditional aircraft uses a cambered airfoil for wings. But if it's just a wing, which has to deal with all of the control and the stability, what kind of airfoil would it be? Think about it. Yes, so it cannot be cambered. He's right. Okay, we eliminated that. So let me just draw the desired pitching moment graph. This is what we require for a statically stable aircraft. This is pitching moment and this is alpha. Now can you try to answer? He is right about why it's not cambered. It's not cambered. The traditional aircraft uses cambered, but the tail and other structures compensate for stability. So your cambered airfoil can, even though it doesn't contribute towards stability, it produces lift. So you can use a cambered airfoil for a full aircraft. But if it's just a wing, you cannot use a cambered airfoil. What about the other two? Sorry? Yes. Yes. Okay. Okay. See, we require the properties of cambered airfoil. Okay. We want it to have lift even at zero angle of attack. But cambered airfoil does not have the stability aspect. So what airfoil does both of that? Symmetrical is, yes. Tell me. Symmetric was something like this. Cambered had a curve. How was the reflexed airfoil? Does anyone remember? Yes. Okay, so reflexed airfoil was, it had an upward curvature towards the end, right? So for when we study static stability, we say that Cm alpha should be less than 0. This is the necessary condition for static stability. Another condition we see is that Cm naught should be greater than 0. This is not a condition for static stability, it's a condition for something else. What do you think it is? What is the why do we need Cm naught? Why do we prefer? It's not necessary, but why do we prefer Cm naught to be greater than 0? Yes, for trimming, can you be a little more specific? Exactly, for trimming at a positive angle of attack. So here, trim at a positive angle of attack. If your Cm naught was negative, it was something like this. So this is a Cm naught negative. This is a positive Cm naught. If it is negative Cm naught, you trim at a negative angle of attack, which is not desirable. We require it to trim at a positive angle of attack. So this is given to you by the reflexed airfoil. Why? So here you have the center of pressure was here and you have the aerodynamic center here, and when you transferred the lift and drag forces to the aerodynamic center, it came with a Cm naught, right? Cm naught, which was always negative. Cm alpha, Cm AC at the AC was always negative for a cambered airfoil. So we cannot trim the aircraft, or in this case just the flying wing, at a positive angle of attack. This is not desirable, hence we came up with a reflexed airfoil. There is obviously there is a reduction in the lift generation capabilities when compared to the cambered airfoil. But the benefit here is that the center of pressure is ahead of the AC. So this is CP and this is AC. So when you transfer the lift and drag forces, you have a positive moment here. Cm naught is positive, right, when you transfer it to the AC. So you have such a curve. This is for reflexed and this is for cambered. Okay, so reflexed airfoil retains the retains better lift generating properties, or like benefit of cambered airfoil was that it has better lift generating properties than the symmetric airfoil. Though there is a reduction in this, it still has better lift generating properties than the symmetric airfoil for the reflexed airfoil. An additional property is that it has a positive Cm naught at its AC, which enables us to trim the aircraft or the flying wing at a positive angle of attack. So the right answer is reflexed airfoil. Okay, so we'll just go over the few shapes that we had seen. This was discussed in the second or third week. So this is a cambered airfoil. So this is a symmetric airfoil, right? We began with that. We moved to a slight camber, deep camber. Then we had so the camber line is something like this. Okay, so it curves up towards the trailing edge, whereas the chord line is this. So what happens? How do we identify a reflex airfoil? It cuts the chord line. Okay, and this is the supercritical airfoil. It's flattened on the top and the camber is retained on the trailing edge. Why did we come up with the supercritical airfoil? What was the benefit? Yes, drag divergence Mach number. You're right. Yeah, drag divergence. It delays the flow separation. So the shock wave, instead of forming here, it forms somewhere aft. So the shock wave forms here. This is why we came up with the supercritical airfoil. Okay. So the next question is, at zero angle of attack, a lift coefficient of a symmetrical airfoil. We have discussed this several times. This is the CL versus alpha curve. So for a symmetric airfoil, how will it be? How will the line look? At zero angle of attack, lift coefficient of symmetric airfoil will be? At zero angle of attack for symmetric airfoil, it will be symmetrical airfoil. What will it be? 0. So your line will be something like this. For a cambered airfoil, it will just be shifted backwards. So you have a positive CL naught. In case of symmetric airfoil, your CL will be just CL alpha. In case of cambered, your CL will be CL plus alpha into alpha. So at zero angle of attack, the lift coefficient of symmetrical airfoil is 0. Okay. For the given graph, Cm versus alpha is plotted. What is the slope of the graph? Very simple. Slope of the graph that is shown here. Okay, so what is the slope? Exactly. Cm alpha is 0. What about Cm naught? What is Cm naught of the graph shown here? It is positive. So is this aircraft stable or unstable, or what is it? Okay. Would you agree if I say it is neutrally stable? Okay, Cm naught has nothing to do with stability. Okay, we just discussed that. Cm naught is only for trimming at some angle, at some alpha. If we want to trim at a positive angle of attack, we require Cm naught to be positive. If we want to trim it at negative angle of attack, Cm naught should be negative. It has nothing to do with static stability. Okay. So here in this graph that is represented by A, capital A, is the aircraft stable, unstable, neutrally stable? What is it? With respect to pitching moment, that is the longitudinal motion. Longitudinal static stability. Is it stable, unstable, neutrally stable? What is it? For static stability, we require Cm alpha to be less than 0. What happens when it is 0? As is shown in this graph. Is it unstable or neutrally stable? Okay. Does everybody agree with it? Okay, can you tell me why you said it's neutrally stable? Can you try to justify? Cm alpha is equal to 0, yes. So how is it neutrally stable? What is neutral stability with respect to pitching moment? Okay, okay, let's just see if this was your ideal graph, right? And you are at some alpha. Now if you perturb this angle, if you increase this angle slightly, so this is your alpha, say this is the alpha that you want to fly at, alpha 1, but if you perturb it by some delta alpha, it goes to alpha 2, and the value here, the slope here will give you a negative pitching moment, right? So Cm alpha is negative. What happens is that it produces a restoring moment, correct? So it'll tend to bring it back to alpha 1. So here if you take the same alpha, you're at alpha 1 and you perturb it and you go to alpha 2, since your Cm alpha is 0, it will not tend to bring it to alpha 1. It will remain at alpha 2. It will establish its new equilibrium at alpha 2. Okay, so it's like the ball in the bowl. So this is statically stable. If you displace the ball to one side, it will tend to come back to its equilibrium position. If the ball is on an upturned vessel and you disturb it slightly, it will continue going away from the equilibrium. But if it's on a flat surface, you disturb it slightly, it will go to the new location and find its new equilibrium point over there and remain there. Okay, so this is statically stable, this is statically unstable, and this is neutrally stable. Statically neutrally stable. Okay. An aircraft with a rectangular wing area S 10 meter square and mean chord C 1.02 meter. What is the aspect ratio of the wing? What was the formula for aspect ratio? How about doing this? How do we go about doing this? So it's a rectangular wing. So let's just write this again. Let's just expand it. So it will be B cross B. Area of a rectangular wing is what is the area of a rectangular wing? Okay, so into the chord. What is the length here? B, right? So length is the span, B. So it boils down to B by C bar. Now the values we have are S and C bar. How do you obtain this from S and C bar? How do you find out? Can you manipulate this term, this B by C bar, to come to an equation that involves S and C bar because we don't have B. We can find out B directly, right? So S is B into C bar. B is given by S by C bar. So what you do here, you just multiply C bar, divide by C bar, and you get S by C bar square. Correct? Correct? Yes. So you have 1.02 square. What is the value? What is the value? It's 9.61. 9.61. So that is the third option. Okay. Okay. Now we'll do a series of 5 questions that has the same parameters here. So this is the data that is given for 5 questions. We'll go about doing that. So let's just read the question. For a propeller driven aircraft with plain flaps, mission requirement data is given below. Vmax is given by 75 meter per second. Takeoff distance is 300 meter. Rate of climb is 7.62 meter per second. Stalling velocity is less than or equal to 25 meter per second. So stalling velocity is 25. The airfoil characteristics. You have the efficiency factor, that is 0.8. That's the propeller efficiency factor. You have the Oswald's efficiency factor, 0.8. Aspect ratio 6. Sigma 1. CD naught is 0.02. CL max is 1.4. First question is, which of the following can be a tentative value of wing loading during stall? Now notice here that they've given you small l. Small l is for 2D aircraft, 2D airfoil. You need to convert it to a 3D airfoil. They've given you a hint here. So we'll proceed with this value. Now how do we go about finding the wing loading during stall? How do we do it? How do we do it? We'll start with how do we just take a moment to think about this? We need to find out the wing loading during stall. W by S during stall. That is what is asked here. Take a moment, read the question and try to tell me how to proceed. Look at the data given to you, read the question and think about it. How do you go about doing this? Where do we start? The stalling velocity is given to you. If that is a hint. How do we start? This is fairly simple, right? How do we begin? Exactly. So we write down the Vstall formula. Vstall is, what was the formula? Okay. So now we have a Vstall, we have CL max. They have asked us to take sea level conditions. So we have rho. We just have to find out W by S. So W by S is rho CL max by 2 into Vstall square. So rho is 1.225, CL max is 0.9 into, what is the value given? 1.4. 1.4 by 2 into Vstall square. So Vstall is less than or equal to 25. So 25 square. What is this value? Just calculate it and let me know. 20.9 to 1.4 divided by 2. What is the value they're getting? 82.3. And what is the unit? What is the unit here? Sorry, what? I didn't get you. Kg per meter square is the one given in the answers, but what is the unit that we get here? W is given in. This equation is valid. It's given in newtons, right? So it will be in Newton per meter square. Convert it to kgs. So what will be the value per meter square? What will be multiply or divide? Yes, so what will be the value? What will be the value? Just look at the options and tell me. Exactly, 49 kg per meter square. Okay, so that is the right answer. You just divide it by G, 9.81. Okay. Let's go to the next question. So for the same data given, we go to the next question. Which of the following can be a tentative value of wing loading during takeoff? So this was wing loading during a stall. Now we have to find out the wing loading during takeoff. They've given you the takeoff parameter. They've given you the power loading. That is horsepower, HP upon W. Again, take a moment and try to tell me how to proceed with this. Read the question. It is wing loading during takeoff. The takeoff parameter is given to you. Try to tell me how to begin. How do you approach this problem? Yes. I can't hear you. Can you just speak a little loud? There's a lot of background noise. You have to first calculate T by W. Is that what you said? How do you calculate T by W? What was the equation? How do you calculate T by W? Okay. I cannot hear what you're saying. Okay, I'll just go with the approach that I have followed, but you can tell me if I'm wrong or if this approach is better. I'm not able to hear you clearly. Okay, let's just take a fresh sheet and start. So they've given you the takeoff parameter. So takeoff parameter is given to you. We know the equation of the takeoff parameter. We just did one question. Where was it? Yes. So it is W by S by sigma CL T naught takeoff by thrust loading. By W, you're right, it's given to us from the, in this case, since it's a propeller aircraft, it will be power loading, right? So you will have, here it's given HP, so it will be power loading, okay? This was the equation for the propeller driven aircraft. Now, we need to, this takeoff parameter is given to you, we need to find out wing loading. That is takeoff parameter into sigma CL takeoff HP upon W. We have the takeoff parameter, we have sigma, we have HP upon W. Right? You have the takeoff parameter, you have sigma. What is sigma? Density ratio, exactly. And you have the HP upon W. What is missing here is CL takeoff. Any ideas how to find out CL takeoff? Uh,
CL takeoff is equal to CL max into VS by
okay. CL max into Did everybody get how this equation came? It's just simple. Just write down the Vstall equation, V takeoff equation, and divide it, right? If you divide it, you get this ratio, right? You get CL takeoff because all the other parameters remain same. Only difference is the CL max and the CL takeoff. Is this clear? That's how we came to this equation. Okay. So let's find out that CL max is, where is CL max? 1.4. Stalling velocity was 25. And what is the takeoff velocity? What is the takeoff velocity?
1.1 Vstall.
Exactly. So we just write 1.1 to 25 square. So what is this value? What is this value? Oh yes, 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 you're right, correct. There will be a 0.9 term here. Correct, thanks for pointing it out. So it's 1.4 into zero point 0.9. Okay, yes, I made a mistake there. So how much will this value be?
1.04.
Okay, so it will be 1.04. So this is your CL takeoff. Okay, now it's straightforward. Just substitute all the values here. Takeoff parameter was 130. What is the value? What is the value here?
Zero three.
18.03. Okay. Okay. So it will be something here. They haven't given the units here, so we are going to presume that it is in Newton per meter, because that is the standard W by S, Newton per meter square. In the previous case, it was given, the options were given in kg per meter square, so we had to divide it by G. In this case, the units are not given, so we'll presume it is the standard units. Okay, so that is Newton per meter square. What will be the climb gradient G given the climb velocity? What was the equation for climb gradient? We just discussed this. G was nothing but how did we find out this value? How do we find this? Think about it. Look at the quantities given to you in the question. Look at the quantities given to you in the question. This is the right equation. How do we find out this? What all are given to you? You have Vmax, Vstall, takeoff distance, rate of climb, efficiency, Oswald efficiency, aspect ratio, CDCL. What can we use here? They've given you climb velocity in this question specifically. So think about why they would have given you that. Try. What is this quantity also equal to? What did we just write? This was written in the previous question. Try recalling that. This T minus D by W is what? T minus... Yes. Okay, if I multiply it with V, it is rate of climb. So it's nothing but rate of climb by V. This is sine gamma, right? We had written this. So you have the rate of climb, you have VC, it's very straightforward. Rate of climb is 7.62, VC is 35.96. Very good catch. What is the value here? Point 2119. So it's 2119. So it'll be this. The right answer. Okay. Is this understood? So your T minus D by W into V was rate of climb. So that is V sine gamma is rate of climb. So from there we have just taken this T minus D by W. That is nothing but your climb gradient. Okay, so that's how we got this equation and we got the value 0.212. Next question, what will be the flight path angle in degrees? From the same set of equations, how do we find this? Vc is given to be the same quantity, so what will be the value of flight path angle? They've asked you to find out gamma. Yes. Sine inverse of what we found. Okay. This rate of climb by Vc. What was it? It was 0.212. So what is the value? Sine inverse of 0.212. What is it? In degrees, how much is it? Yes, 12.23 degrees. Okay. Next question. What will be the thrust loading during climb if the Vc and power loading are given to you? What will be the thrust loading during climb? This equation is a direct equation, if you remember it. For a propeller driven aircraft, remember that. Propeller driven aircraft. It was a direct equation that was given, thrust loading equation. Thrust loading equals power loading and exactly. Huh. So need by V. This was the equation. Eta into 550 by V into the power loading. Straightforward equation. Let's just substitute the values. Okay, just ignore that this is given in feet per second. Just take all metric units, so it will meter per second. So it will be 1 by 7.5 into eta is 0.8 into 550 and Vc is 117.99. What will be the value? 0.8 into 550. I'm getting 0.49. Is that the right answer? Is everyone getting that? Yes? Eta is given here, right? That's what you were asking, right? Okay, let's just presume that it is the efficiency factor. If you use that, you're getting 0.497. So that is this one. Next, what will be wing loading during climb? Again, ignore this unit. It will be meter. It will be Newton per meter square. Here again, it will be Newton per meter square. Okay. Take metric units. What will be the maximum wing loading during climb? So we had the climb equation, we had the wing loading, it was quadratic in wing loading. Do you remember that equation? Yes. Yes. Yes, that is the one. Let me just write it down. So minus square root of d by w minus g minus, what was the quantity here? for CD naught. If I'm not just correct. I'm not really sure what the denominator was. 2 by okay, let's just try finding out these values. So we need thrust loading. They've asked you for thrust loading. So let's take that here. And they asked you for what they asked? Wing loading. Okay. So let's just try finding out each quantity individually. So it will be thrust. How much will this be? Thrust loading during climb. We just found it in the previous question. 0.497. Is it different? VC is same, right? Okay, it's different. It's different. Okay, let's just calculate it again. Okay. Okay, let's just do that again. What was the equation? So the power loading was given by 1 by 7.5. Okay, we'll just find out thrust loading separately. That was 550 BC into the power loading. So how much was that? It's 550. Yes.
If we convert that feet per second into meter per second, it's coming the same value. 35.96 meter per second is
Okay.
equal to 1.7
Okay. Okay. So then we should have used that quantity here, is what you're saying. Okay. So let's just calculate it with 35.96 here. Okay. Let's just do that. So this was 0.8. This is 35.96 into this was 1 by 7.5. Okay. So what will this quantity be? 550. I'm getting 1.63. Correct me if I'm wrong. Okay. So T by W minus G will be 1.63 minus G was, we've already calculated this. I think that was the same velocity. Yes. So G is 0.2. By EAR is 4 into CD naught is 0.02 pi, efficiency factor was 0.8, aspect ratio is 6. 0.8 into 6. How much is this quantity? How much is this value? Zero point zero zero. Is this right? Now let's just do the denominator, that is 2 by Q by E AR. 2 by Q is given as 16. 2 by E is 0.86. And that will be
There is a difference in the unit because for the V we are taking meter per second and the unit system.
okay. I'm not sure. Huh. I'm not sure if I've changed some of them. I've not changed some of them, so the answers might not match. Let's just proceed with the calculation, okay? So when the question is given to you, I was just trying to change a few values. I didn't change all of them. So that's where the error has come. Okay, let's just proceed with the calculation. But when in your assignment you follow this convention, okay? Just convert everything to the same units. Okay. Okay, let's just proceed with this for now. The answers might not match. We'll just go through the process. So if I substitute all of them into this equation, so I'll just write it here. So W by S is less than or equal to, that was 1.4181 plus or minus square root of 1.4181 square minus 0.0053 divided by 0.0083. What will this value be? It will be plus or minus 170.63. On this side it is 1.181. Okay, so they've asked you for the maximum possible. So you add these quantities, don't take the subtraction. I have messed up the units, which is why it has come to such a large quantity. It will not be so large. But if you proceed with this, you get something around 340, 341. Okay, so it will be less than the summation because they've asked you for maximum wing loading. So just take the positive quantity. Just make sure of your units when you solve the assignment questions. But the process is clear, right? Yes.
When we take the units in the same order, say pounds, value is coming 67.6.
Okay. Okay. So we should have just taken VC as 117.
117.9.
Okay. Okay, let's just try doing that then. Then our T by W of the previous case was valid, right?
So
Okay. 117.497. 497. That will be 0.497 minus 0.2119. 0.285. Yes, is that right? Okay, let me substitute those values. values here. As 0.285, 0.285. What does it come to? 67, right?
67.6.
7.6. Okay. And the unit in this case will be pound per feet square. Right? Okay. So is that given here? Okay, that is given here. So yeah, so the question was right. We should have just proceeded with the units given in the question. Is everybody else clear with this? We should have just converted this meter per second into pound per feet. And feet per second. Just convert this into feet per second. Okay, which the value here. So our T by W of this case we could have retained. Is everybody else clear with this? Is there any question? No. Okay, let's move on to the next question. Now, look at this airfoil. Just observe it for a minute. Graphs. So, what the question basically will be is to identify some graphs based on this airfoil. Okay. So, the red line is the shape of the airfoil. This greenish yellowish line is the cambered line. Okay, so let's just look at the graphs. Now they've given you 4 graphs. Try identifying what each of them is. The question here actually was which is the CM versus alpha graph. But let's just try identifying all these graphs, what they represent. Looking into it. If you can identify CM versus alpha, let me know that. If you can identify any of them. So these are actual values from experimental tests. So just look into it. Try reasoning. There is no reflex. It is a cambered airfoil. There actually may be a reflex, but okay, no, it's a cambered airfoil. It's a cambered airfoil. So what do we know for a cambered airfoil? CM versus alpha graph, how will it look? It can be stable or unstable. That is not the question here. But what other identifying marks can you notice? Yes. So in which of these graphs can you see something like that? Fourth one, yes. So this is the CM versus alpha, where you have a negative CM naught, and if you look at the positive variation of angle of attack, it is a slope with a positive. The slope is positive. The curve with a positive slope, so it is not a stable airfoil. Okay, so let's try looking at the other graphs. Can you try identifying it? We have 2 parabolas here. This is also parabola. This is also parabola. So if that is any hint. Yes. So which one would be? Both of them, yes. Both of them have drag. CD. Try getting it studied.
Is it
No, no, not the available power. So, okay, I should have drawn a line here. This is somewhere around. This is somewhere around 0. Okay. So this is a positive. What can you think about that? Third graph, you mean this one? What did you say it was? Okay, it is CD versus alpha, but yes, CD versus CL also will look like this. Yes. So the CD versus CL is a parabolic equation. So you have CD equal to CD naught plus KCL square. So if the variation with CL and alpha would look the same. Yes, it's a parabolic equation. This is right. This is CD versus alpha. Similarly, what would this be? It's a parabola in the other direction. So you know that the CD will be on the other axis, right? Yeah, so it's just that. It's the drag polar. Drag polar. Yeah. So this is the zero axis. I should have marked that. What will this be? The first graph? Exactly. It's CL versus alpha. You can see that it has a positive CL naught. It's a cambered airfoil. It will have a positive CL naught, and it is fairly linear in that flow regime. So uh, CL versus CD, CD versus angle of attack. This is the values. Is everyone clear with how we came to these conclusions? Apart from the two people who were answering, the others, are they clear? So this is the typical profile of a drag polar. Okay, so you have this region here. It's called the laminar flow region, laminar bucket. I'm not sure what the term was. Similarly, here you have the drag bucket, this area. So try looking at these typical things in the graph. So you have CM naught negative for a cambered airfoil. That is how we identified this one. You have a drag bucket in case of the drag graph, and any equation with drag and CL will be parabolic. So when you see a parabolic curve, try writing down the equation and see which is on which axis. And here it was a linear variation with alpha, positive CL naught. So you knew it was CL versus alpha. This was a cambered airfoil. Now let's look at a simpler case of a symmetric airfoil. This should be easier to do now that we have done the cambered airfoil. Just look at the graphs, try telling me which is which. Just remember the points that we had seen in the previous case. Fourth one is CM versus alpha. Okay, okay. Is it? Why is it the CM versus alpha? Okay, okay, let's go with that. CM naught is 0. CM naught is, if this is the CM versus alpha, this in this case also it's 0, right? Okay, so somebody else says this is CL versus alpha. Okay, what about the other graphs and what about the other participants? Just remember what we did in the cambered airfoil, relating it, and what changes if it's a symmetrical airfoil. First is CL by CD, okay. Then CD versus alpha. And what is this? This should be CM versus alpha. Okay, any other answers? Any other guesses or justifications or anything? So if this is CM versus alpha, what is happening at these points? Let's just take the positive angle of attack variations. What is happening here? There is a change in the slope. Why is that happening? Just try reasoning. Why do you think it's happening? There's a sharp change. What what do you think will happen at that point? What do you think happens at those peaks or the sharp changes in the graph? It's called pitching moment reversal, which is evident here. What happens? Can anyone try guessing if this is the CM versus alpha? So yes, this is the CM versus alpha curve. It's not this. This is the CL versus alpha. It's almost linear in that region. So now let's try justifying why this peak occurs, or why this change in switch or reversal of the pitching moment at those points. Any idea? Just think about it. What do you think would happen there? What do you think happens at those points? Okay, so at those points you have this flow separation, the boundary layer separation. This is what is characterized by these pitching moment reversals. Okay, at these peaks, that is where the flow separation occurs. Okay, so for symmetric airfoil, it is symmetric. For other airfoils, it'll change. It will not be the same. So you can see that in the previous case as well. Here also there were these sharp peaks. Since it's cambered, we are not able to justify it properly that it's symmetric. It's happening here on the upper surface, here on the lower surface. But in the symmetric airfoil, you can see it very clearly. It's more or less symmetric, just like the CL versus alpha curve. Just like all of the curves, in fact, they are all symmetric about some axis. Okay. Okay, now let's go back and try doing another aerodynamic center calculation, because again I thought there was some difficulty in solving it. So let's take a relatively simple problem this time. So last time it was tapering about the quarter chord. There was tapering about on either side. This time let's take something that tapers about the trailing edge. Okay, so it should be easier this time. Okay. This angle is given as 37 degrees. This is 675. This is 675. This is 110. And this is 800. Okay, so now let's find out XAC. Find out C bar and XAC. So how do we go about doing this? We divide it into two sections. Okay, so this is section 1, this is section 2. We should be able to do it quickly this time. The other one was more complicated. So for section 1, what is the area? What is the area? You try telling me area of a trapezoid. What is the value? Yes. So how much is that? Plus quantity. So that is, let's say, x. How do you find out that x? 800 plus x into 675. How do you find out this x? This is simpler than the last time. How do you find out x? Everything is straightforward here. How do you find out that quantity x, this value?
Is this 110?
Yes, it's 110. Yes.
So, can we check this line, this opposite to the line where you have written 110 as
We have not calculated c yet, right? So we don't know what the value of c is. To calculate c bar, we need x. How do you find out x? This is x. How do you find that? This is straightforward. If you understood the previous week's problem, this should be much easier than that. There's an angle given to you over there, the sweep angle of the leading edge. Try using that as a hint. No? Okay, so let's this distance as y. Can you find out y? Can you do that? Okay, but how do you find out this y and x? Exactly. Tan of 37. Did you understand that? Tan of 37, it's not just tan of 37, tan of 37 into 675. Yes? Is everybody following this? Yes. So what is this value? Five zero 8.65. So what is x? What is x? So it is just, let me write that. It's 800 minus y, it is 291.3. Okay, now we can substitute that x here to get the area of the first section, which is half 800 plus 291.3 into 675. So this will be a huge quantity. What will it be? Three six eight three 330.9. Okay, next we find out the aspect ratio. Aspect ratio of the first one is b1 square by s1. What is b1? What is the span of the first section? 675 square by S1 is 1.23. So the aspect ratio is 1.23. What about taper ratio? Taper ratio is tip chord by root chord. What is the tip chord here? Yes, 291.3 by root chord is 800. So this value is 0.36. Okay, using this you can find out the C bar, the mean aerodynamic chord of the first section. What was the formula? Does anyone remember? Just 2 1 plus yes, so let's just substitute the values. 2 by 3 CR1 was 800 into 1 plus 0.3 plus 0.36 squared 1.36. So what is this value? Someone calculate and let me know. What is the value? Okay. 585.14. Okay. Now let's do for the second section. Similarly, S2 is what? Again, it's a trapezoid, half. What is the value? 291.3 plus tip is 110 into 675. What is this quantity? One, 38.75. Okay. Okay. Aspect ratio of the second section is B2 square upon S2. Span of the second section is the same. It's 675 square upon S2, which is 3.33. 3.36. Okay, next is taper ratio. Lambda 2 is CT2 upon CR2. What is CT2? Tip chord. What is the tip chord of the second section? 110 and root chord is 291.3. So this comes to 0.37. 0.37, is that right? Yeah. Okay. So let's find out C2 bar. The same formula, just find it out quickly. There's a value here. What is the value? 213 213.6. Okay, so now how do we find out the mean aerodynamic chord? How do we find this out? We have it for section 1 and section 2. Now how do we find out for the overall section? How did we do it last time? How did we do it last time? If you have C1 bar, C2 bar for 2 sections, how do we find out for the overall section? We did it just last week, similar problem. In fact, a much more difficult problem than this. How did we do it? It was a weighted average, right? Do you remember that? It was a weighted average. We discussed centroid, center of mass concepts. So what will the value be? What will the equation be? How do you find the weighted average? It was S1 C1 bar, S2 C2 bar by S1 plus S2. So what will this value be? Just do the calculation and let me know. Is everyone following this? Do you remember this? It was the weighted average. It's like the centroid. Okay, so just tell me this value. So you have S1 here. This is S1. This is C1. You have S2 and C2. So just tell me what this is. Substitute these values and let me know what the C bar is. What is the value? What is the value? It has to be less than 800 and greater than 110, right? Yes. That is the right answer. It's 485.45. So that will be somewhere around, let me just erase this. So section 1, that will be somewhere around here. So that is your mean aerodynamic chord, C bar. So 1/4 of that would be your aerodynamic center. So that is your aerodynamic center, AC. Now we need to find out XAC. How do we find out XAC? XAC. XAC is, I just should denote it here. With another color. So this quantity is XAC. How do we find out XAC? Sorry. How do we find out XAC? So we know this value. How much is this value? What is this value? The one in purple. How much is that value? What is the length of this whole red line, this mean aerodynamic chord, this whole red line, what is the value? What is this?
C bar by 4.
Yes, so the small purple line is C bar by 4. Okay, so C bar by 4 is given in purple. Okay, then what we need to do is find the remaining distance. We need to find this. The green line plus the purple line gives you XAC. How do you find this green line? 800 minus C bar, right? Green line is 800. Exactly. So the green line is 800 minus C bar. And you add these two, you get the blue line. So that is 800 minus C bar plus C bar by 4. That is your XAC. What is the value? It comes to around 400 something. Just quickly do it. It's 435, right? So X bar XAC is 435.9. So that is the value. Did everybody follow this? How we got 800 minus C bar plus C bar by 4? It's very simple. It's just the summation of the green line and the purple line. The purple line is 1/4 of the, the green line is the entire distance minus the chord. Right? Okay. Is there any doubt? Do you have any questions from this? Okay, then we've come to an end of this lecture. Do let me know if you have any questions. We'll meet on Tuesday. We'll discuss the week 8 lectures and assignments. So why MAC? There was the formula, right? 1 minute. Let me just look at the previous. 1 minute. Okay, I'm not sure what the equation was. Let me just see it. I had kept it in the last lecture. Just a minute. I'm just searching for the equation. You were right. It was that b by 6 equation. Let me just share the screen. So this was the equation YMAC. So that was the equation, b by 6 plus 2. Yes. And just like we did the mean aerodynamic chord, if you had to find out the aspect ratio or the taper ratio or any other parameter of the entire section, you do the same weighted average. Okay. So mean aerodynamic chord, we did S1 C1 bar plus S2 C2 bar by S1 plus S2. For aspect ratio, it will be S1 AR1 plus S2 AR2 by S1 plus S2. Similarly, for any such parameter for the entire section, you do a similar weighted average. Okay. Any other questions?
Can you again show the YMAC formula?
Just a minute. Yes, here it is. It's b by 6 into 1 plus 2 lambda by 1 plus lambda. Why we focus mostly on the XMAC is because when we see stability, the pitching moment, all of those stabilities, the neutral point distance, it's all from the leading edge. So that value is XMAC. Okay. Any other questions? I don't think so, no. Such questions will not be there in the exam, but this will help you in designing the aircraft in general.
Okay, then what sort of questions will be there in the exam?
It'll be just like your It'll be just like your assignment questions. So you will have those multiple choice questions and numerical type questions. It'll be short, just like your assignment questions. Any other doubts? Okay. If not, then we have this lecture, this session. So we'll meet on Tuesday. Thank you.